big problem. Okay, the connection got lost again. Sorry about that once again. This is a consistent problem now. And so we can just solve this now. We have almost done with this part. And this gives us, and we can also cancel out this half, half and half. So we get that our VF will be equal to our capital M divided by capital M plus small m times omega naught. So we get our final angular velocity of our A will be equal to capital M plus small m times omega naught. And come to the next question. So in this question, it is said that find the frequency of small oscillations of a marble of radius B rolling in a shallow dish of radius R, where R is much larger than B. So for this we can just draw an approximate figure, and suppose this is our shallow and its radius is given as capital R. Suppose this is the center of this and we have a radius R, and we have a marble of small radius. So let us suppose this is the marble and its radius is given as small b, and let us suppose it is making an angle of theta which is small over, and so in this case let's assume that the radius of curvature of our this dish is represented as our O, and the marble initial position of the marble will be obviously somewhere here at the lowest point, and we say that its center is represented as C. Okay. And the so we can say that our distance from O to C therefore we can say the distance our OC, let us say represented as rho, and that will be equal to our, let us call this as point of contact at P. So that will be our OC, that is our rho will be equal to OP minus PC. OP minus PC. So we get our rho is equal to R minus B. Okay. And here we have to keep in mind that our this R is much larger than B. We can deal that later on also. And for this point of contact P, the value of theta is equal to 0. Okay, when the marble is at the equilibrium, or we can say when it rests at the bottom. So we can say that the marble rests at the bottom of the dish and we have this value of theta will be equal to 0. And during the oscillation, this marble center C moves along the arc, and theta is nothing but the angular displacement with respect to the vertical. And so here we are going to deal it with the energy format, and this is point P, and this point is, let us call this as a P prime, okay, in order to just differentiate it. So we can say that the potential energy and this potential energy, we can say that at the lowest point, okay, so let us find out its potential energy at point P prime. And for that, let me redraw this figure. So we have this as our P point, and this point is our P prime. Okay. And therefore we can say that the vertical height of C above its lowest point. And let us also draw the point C. So this is C, and it is going to move like this. So therefore the C is also going to follow same path. So we are going to head, this is our center of the marble. Okay. And this is point O, and we have angle of theta. And we can just draw this as our horizontal plane. Therefore we can say that the position of C relative to O is along the radius rho, is along the radius. And we can also say that the vertical height of C above its lowest position let us call this as our H, and this H will be equal to rho 1 minus cos of theta. And so in this case, okay, so we can say that the vertical coordinate, since the vertical coordinate of C is rho cos of theta, and vertical coordinate of C is rho cos theta below our O, and therefore we can write that it's 1 second. Rho is our okay. Okay. So now we can find out the potential energy because we know our H. Yes. Therefore we can say that the potential energy and let us call this as our V will be equal to mgh, and h we already know, so we can write this as mg rho 1 minus cos of theta. And for small oscillation we can write that for small oscillations we can say that our cos of theta is approximately equal to 1 minus theta square upon 2. And this expression is basically based on the Taylor's series, okay, because cos of theta is basically 1 minus theta square upon 2 factorial, and plus theta 4 divided by 4 factorial, and so on. Okay, so therefore we can say that our theta naught, and this is based on the Taylor series. And therefore we can just substitute this, and in place of our 1 minus cos of theta, therefore we get that our V will be equal to, we have this as mg rho and 1 minus theta square upon 2, and this 1 and 1 cancels out, so we get this as our half mg rho theta square upon 2. So this is our potential energy. And now we can find out the kinetic energy. And kinetic energy, it is given that marble is rolling without slipping, so therefore the motion will be inclusive of both the translational motion about its center C as well as the rotational motion about the center C. So we are given that there is rolling without slipping, so we are going to have both energies. We are going to have translational, and we are going to have rotational. So first of all, let's find out the translational. We have translational kinetic energy, and this translational kinetic energy, let us call this as E translational, and that will be equal over half m v c square. Okay, and we know that our this marble center C is moving along a circular arc of path radius rho, which I have already drawn here. Okay, so it is moving in a circular arc, and this is, we know, is our rho. So this is our rho, and this will be also our rho. So it is moving in a circular arc of radius rho. So we can say that our marble center C moves along a circular arc of radius rho. Therefore, we can say the tangential speed of C that is our center, which we call that V of C, will be equal to rho and first derivative of our theta. And so we substitute it in this equation. Therefore, we get our translational energy will be equal to half m rho theta dot whole square. So this comes as half m rho square theta dot square. And now we come to the rotational kinetic energy. This was our translational, and we have a rotational kinetic energy. Let us call this as R rotational. And so in this case, there is a pure rolling motion without slipping. Okay. And therefore, the velocity of the point of contact, that is our P, relative to the dish is 0. Okay. So we need to find out the marble's angular velocity about its center C. So we can say that we are having pure rolling without slipping. Therefore, the velocity of P relative to the dish is 0. Relative to dish is 0. Okay. And we are going to find out the angular velocity, that is omega, about its center C. We can just calculate it. Okay. And so if the relative speed of this point P is 0, so we can say that this point P is stationary. Okay. And the marble rotates about its instantaneous axis through the P. Okay. And the distance between C and P is given as B. Therefore, we can say that the velocity of C which we have denoted as Vc is equal to rho times our first derivative, and the angular velocity about point P angular velocity about point P, we can use our rolling without slipping condition, that is omega P is equal to Vc upon the radius over B. Okay. And from this equation we can easily substitute our Vc, so we get our omega P is equal to rho theta naught first derivative and divided by our B. And therefore we can say that one second. Yeah, so we can find out the total kinetic energy in the rotational, which can be given as our half I omega square, and here omega is nothing but our omega P, which we just find out. Therefore we can say that our E rotational will be equal to our half I omega P square, and we know that the moment of inertia of I is about the center about the marble, which is 2 by 5 times m B square. So we get this as our half 2 by 5 m B square, and this gives rho theta dot P, and this is a whole square. Now this is here 2 and 2 cancels out, therefore we get our E rotational will be equal to 1 by 5 m, and this B square and B square also cancel out, here it will be square, and this is m rho square theta dot square. So therefore the total kinetic energy let us call this as K, will be equal to energy translational plus energy rotational. So we get this as K is equal to translational is our 1 by 2 m rho square theta dot square plus rotational is 1 by 5 m rho square theta dot square, and we can take this LCM will be 10, so this will be 7 by 10 times m rho square theta dot square. So this is the total kinetic energy, and now we can use the energy conservation, and so energy conservation basically means that the total energy is going to remain same. Okay. Therefore we can say that our energy conservation, and we can say that our total energy, that is our E, is equal to, one second, potential energy is our V. So we have V plus K is our V plus K, and this energy will be our constant. And we substitute this both V and K, so we get our energy E is equal to, and V is our half m g rho theta dot square plus 7/10 m rho square, and this is our theta dot square, and this is equal to constant. So differentiate it, we get dE upon dt. This will be giving us one by 2, and we have this as mg rho, and this will be twice theta dot, and we get this as our, one second, I think energy is, there is no here it is, and there is no dot, so we get this as, so there will be no dot here, sorry, here it will be, but here it will won't be, this is not dot and this is not correct. Okay. And this comes as our first derivative plus 7/10 m rho square, and this comes as 2 theta dot, and theta double dot is equal to 0. And now it is only the simplification. We can take our m cannot be equal to 0, so we can just remove our m, and we can also remove our theta dot, and here 2 and 2 cancel out, this goes by 5, so we are left with only mg, we can say this here was g rho theta plus 7/5, and we have this as rho, we can also, one rho also goes away, so here it is only g theta, and this is 7/5, and this is rho double dot is equal to 0, and we can just make in the standard format. So this gives us a double dot plus 5/7, and this is g upon rho, and theta is equal to 0, and this is nothing but equation of our SHM, okay, which is standard is our double dot plus omega square theta is equal to 0. So we can say from here that our omega square is equal to 5/7 and g upon rho, or we can say that omega is equal to 5/7 g upon rho, and from here we can find out our this frequency also. Okay, we can, and this is square root, we can substitute value of rho also, so we get this is omega is equal to 5/7, and the rho is our r minus b and square root, but we know that r is much larger than b, therefore we can say that our omega is equal to 5/7 g upon r and its square root, and from here we can find out our the frequency, cyclic frequency, that is of f will be equal to omega upon 2 pi, which gives us 1 upon 2 pi square root of 5g upon 7 rho. So this completes today's question, and yeah, that's all. Thank you.